This video is an introduction to simple summary statistics in R, and we also will be looking at the use of packages. So let's start by just doing some simple arithmetic. So let's just take 5 and add that to 8. And what I need to do now is to either click on Run or hit Command on my Mac, Return. If you're on a Windows machine, then Control Return. I'll just hit Command Return, and you can see that from my script window here I've issued a command. The command is repeated down here in the console, and the answer is given in the console. So 5 plus 8. Now R doesn't care when you're doing these simple sorts of arithmetic whether or not you have spaces or not, so that works just as well. One of the neat things about RStudio is that you can annotate your scripts, and what you do is to hit the number symbol, and then everything after the number symbol becomes invisible to R. So it's visible to you, of course. So I can just say simple addition, and so I can still run the command, but in simple addition shows up down here, but it's not run. All that happens is 5 plus 8 equals 13 is shown. So it's very useful when you're trying to keep track of what you've done in an R script to annotate it. It's particularly valuable if you are collaborating, so that your collaborators will know why you issued a particular command at a particular time. And you may find as you watch this video that you want to replicate various commands that I'm putting up, and you might want to annotate them. I won't take the time to do the annotations myself, but you may find that very useful, using the pause button to slow down, stop the video when you want to make an annotation on your particular copy of the script. So subtraction, as you can imagine, done in a similar sort of way. So 45 minus 34, and then we get 11. For multiplication, we don't use X for multiplication. We use the star. So 34 times 45, and there's our number. And again, we can put spaces in if we want. I can put a space and then no space. I'm still going to get that same answer. And finally, of the 4 major operations, division, using this backslash like so. Those all work very well. We can also raise numbers to exponents. So we take 3 and we're going to raise it to the 4th power. So we use the caret sign, the 4th power, and we get 81. There's no reason that either the base or the exponent have to be integral, so we can say 3.21, and we'll raise that to the 4.223 power, and we get our number there. Square root, SQRT, and that's how you calculate the square root. We can also take logarithms, so we could take the log of 100, and we know 100 is in base 10 is 10 squared, so we might imagine that the log of 100 should be 2, but in fact we see it's 4.6, and that's because the log command is based on natural logarithms, so it's based on the base e rather than base 10. So if we want to calculate the logarithm into base 10, we would use log 10, and we do 100 there, and we get the familiar 2 for our exponent there. One of the powerful aspects of R is that you can define objects. And an object can be a simple numeric value, it can be a command, it could be a data frame, a data set, it could be a graphic, it can be a summary. But what we're going to do is to just define a very simple object here. And to define an object, you first state the object. We'll call it X in this case, and then you need to hit the less than sign and the dash, a hyphen. So it's essentially a left-facing arrow, and it's read by people that use R as gets. So X gets the value of, and let's just give the value 56 to x. So I'm going to define an object x, and x is equal to 56. And you can see now that x has popped up here in my values. In my working environment here, it shows up as one of the values that I have defined. Let's set up another object, and let's call this one y. And I'm going to define y as a product. So y is 47 by 12. Now when I run that, I don't see anything. I just see that y is equal to 47 by 12, but it doesn't tell me what y is. If I look up here, I can see what y is. The value of y is shown there. If I want to see the value of y, if I want to print it to the screen, all I've got to do is just to type y and hit run, and I get my 564 there. Once we've got objects, we can do other things to them. So let's take z, and z is going to be equal to x plus y. And again, z is showing up here. I've got 620, and you can see adding 56 and 564, and we get to the 620. If I wanted to see it in my console, I would just type z and hit return, or command return, and then 620 pops up right down there. So objects can be used arithmetically. We can add objects to each other, divide them, and so forth. Let's talk about vectors. Vectors are a series of either numbers or characters in R. So a vector has some length, and a requirement of a vector is that all of the constituents have to be of the same type. So we can have a vector of numbers, or we can have a vector of characters. But let's just set up a vector, and let's just set up one called, we'll call it v1. And what I'm going to do is to make that vector, I'm using the C, as C stands for concatenate. So I'm just going to put together a bunch of numbers here, like so. And I'm just telling R that I want to make a vector, essentially one column of data, and it has all of those components. So I'm going to run that, and v1 shows up here in my global environment, and you can see that it consists of 9 numbers, and the numbers are printed out like so. So that's one way to create a vector. There are other ways to create vectors. Let's do a vector 2, and this time it's just going to be a sequence of numbers. So I'm going to say I want all the numbers between 31 and 46. So all I've got to do is to put in numbers like that, separated by a colon, and I run that, and now I have a second vector, and this has 16 different components starting at 31 and ending at 46. I can also do a character vector, so let's just do an example of that. And again, I would use my concatenate function, but if I'm adding characters, then I have to enclose them in double quotes. But the neat thing about RStudio is that if you have an open double quote, it knows you need a closed double quote. So when I hit double quotes, I get 2 copies. So let's just make a series of names. So we'll have Joe, and then I hit So we've got four different names there, and if I hit the run on that, then I've got my character vector here. You can see CHR, and I've got the 4 different components that you see there. Now, remember that a vector cannot contain both numbers and integers. Let's see what would happen if we try to add a number to vector number 3 here, v3 here. So let's add 56 to that and run, see what happens there. Well, it did run. We have that vector now, but what R did was to say, all right, I've got both a parent number here, and I've also got character data here. I'm going to have to convert this number to a character. So this 56 is essentially the symbols 5 and 6, but it doesn't carry the value of 56 of 50 plus 6. That's not the same. So this is treated as a character rather than an integer in this particular case. But when we do have numeric vectors, we can do all sorts of things with R to calculate summary statistics. So one thing that we might want to do is to figure out, well, what's the mean value of V1? And so all I've got to do is say mean V1, and then down in my console it is 6. So that's the average value. I might want to know what the median value is too here. So again, you might want to annotate some of these, determine the average value, like so, just to help yourself in subsequent viewings of the script. So there's the median. We can also determine the minimum value of V1. And of course, you know, if we've got 9 or 10 values, it's easy to do that. But if you've got a million values, then having a command to let you know what the minimum is very handy indeed. So the minimum was 2, and of course there would be a maximum as well. We could also calculate the standard deviation of the numbers. So the standard deviation was 2. You could also do the variance if you wanted to know what that might be. The variance is 4, which is normally, the variance is the square of the standard deviation, so that works out for us well. A very useful series of numbers is the so-called 5-num system, V1, and we're going to get 5 different numbers here. The first number is the minimum, the last number is the maximum, the middle number is the median, the 5 is the 25th percentile, the first quartile, and 7 is the third quartile. So 25% of the values are between 7 and 9, 25% are between 6 and 7, 25% are between 5 and 6, and 25% are between 2 and 5. Now these 5 numbers are very useful because they are used to create what's called a box plot, or perhaps you've seen those, and we'll look at those in subsequent videos. But that's a very useful series of statistics, the 5-number system you can see there. Now, a single vector is not all that interesting for most analyses. That typically we're going to have a number of different variables. So instead of looking at just vectors, what we're going to be spending most of our time doing is looking at what are called data frames. So let's just describe what a data frame is. It's a series of vectors of equal length. So you can think about a data frame as being a data set where some columns might be all numbers, and another column might be dates, and another column might be characteristics, but they're all put together and they all are of equal length. In R, there are a number of built-in data frames that are very useful for teaching and for exploring the power of R. If we hit data and we just leave the open and closed parentheses with nothing inside, that's essentially a wildcard. So it says show me all the data that are built into R, and you get a long list of the data sets. So you can see various data sets, some of which may be enticing for you to look at, but all kinds of data sets to take a peek at. And what we're going to do is to look at the iris data set. You'll notice up here that a second tab has opened up, so it's showing the R data set. So if I want to go back to my script, I just go over here. And by the way, what I see there is that I have a little asterisk there, and that means that I have unsaved changes. In fact, I've never saved this particular script because it's untitled. And what I'm going to do now is just to save it as, I'll just call it demonstration, went to a particular folder in my R directory there, as you can see. So I'll save that, and now I've got that saved. But as soon as I add an additional bit of information, then I'm going to get that red asterisk back. But let's take a look at one of the data sets called the iris data set. And so iris is going to show up here in my global environment. When you open up one of these data sets, you want to do a little exploring just to see what you have. And one thing you might start with is asking, well, how big is the data set? And so I'm going to ask for the dimensions. So that's just DIM. And this tells me that the iris data set has 5 different columns. So that's essentially 5 different vectors, right? And there are 150 rows. So each of those vectors has 150 entries in it. You can see that shown up right here as well in the global environment. If I wanted to just know what the number of columns was, I could just ask for in col 5, and I could do in row to know what is to ask for how many rows there are, and there are 150. It's always good to take a look at a few of the values. Now, if I wanted to, I could just type iris and have it print to the console, and I can do that because there are only 150 values, and I can scroll through and see all the data that you can see the data there. But if you have a data frame that has 1,000,000 rows, then printing it to your console is not going to be very useful. In fact, you're going to run out of memory anyway. So a useful way to take a look at some of the data is just to take a look at the head. So just do the head command of iris, and what we're going to see are the first 6 rows. So we get the column names, sepal length, sepal width, petal width, species, and we get the first 6 values. It's always a good idea to look at the last bit of the data frame as well, because oftentimes people will put in little explanatory entries that may not be useful, or in fact could confound your analysis. So it's always good to look at the tail as well. So if we do that, we have the last 6 values in the data set, again with the appropriate column names shown there. We can also look at the structure of the data frame, and we use the structure command, which is just str. And people that use R call that the stir command. So we can issue a stir command, and we do that, and what we're going to do is to see descriptions of each of the 5 columns of the data set. So we see sepal length is a number, sepal width is a number, petal length is a number, and petal width is a number. Sometimes you'll see int here for integer, but obviously these are not integers, but rather numbers with floating decimals. And then finally we have a variable here called species, which instead of being a character is said to be a factor. And a factor is a classification variable that has a limited number of possible values. In this case, we just have 3. There's Setosa, versicolor, and virginica are the 3 species of iris that are being considered. So stir gives you an idea of the structure of your particular data frame. So what we can do now is to take a look at some components of the data frame. And let's just say that we were interested in knowing what is the mean sepal length in this particular data frame. So we know we have 3 species, but we're going to meld them all together. We're not going to try to separate them out at this point. So we're going to say, what is the mean of petal width? Well, we can't just say petal width because we have to let R know what data frame we're dealing with. And by the way, this is a data frame. We can see it from this stir command, data frame here with 150 observations, 5 variables. So what we're going to do is to say iris, and then we have to tell it which of the columns we're interested in by specifying it after the $sign. So I'm going to do mean of iris, $sign, petal width, and I get my value there. There's the 1.19933 that you can see down below. We could also do median, just like we've done earlier. This time we'll do petal length, and we get that value there. A very useful feature is the summary command. And what the summary command will do is to give you some summary statistics on every one of the columns that you have in a data frame. So we're going to run summary on the data frame, and you can see that for sepal length we get the 5-number system we talked about earlier, the minimum, the first quartile, the median, the third quartile, and the maximum, as well as the mean. So that's calculated for each of the, for sepal length, for sepal width, petal length. And then for the factor, we note that there are 3 factors, and each of them is found in 50 rows. So that's a very useful way of taking a look at the data. There are other summary statistics that might be of interest to an investigator. And what we're going to do is to add some functionality to this copy of R by installing an extra package, a different package. So we're going to say install packages. It's the usual way you install a package. And we're going to install the psych package. So install packages psych. We'll run that. And you can see down in the console that my package has been downloaded. And in fact, what it's going to do is it's going to show up here in my list of packages. So there is psych, but it is not active. I need to activate it, and there are 3 ways we can do that. And what I normally do is just to use the require command. So I'm going to require psych. And now watch over here what happens when I hit require psych. That it gets a check mark. So now it says that it is being used. It's loaded into R. Another way of doing that, we'll declick it. That's one way to. A second way of doing it is just to go into your packages and just to click the ones that you want. So that's an easy way to do it too. But there's a third way, and that is instead of using the require command, is to use the library command and get the same thing. Now, if you want to find more information on the psych package, then just hit the question mark psych, and what you will see is a very nice help document here talking all about the various ways that you can use psych. But what we're going to do is just to use a couple of aspects of it. One is that instead of using summary in psych, they use describe. So we're going to say describe iris. And so here we see the 5 different columns that we have, the 5 different vectors. Each of them is 150 in length. That's a requirement of a data frame, that the vectors all have to be the same length. There's the mean, standard deviation, median, the trim mean. That means that the top 5% and the bottom 5% are excluded, to exclude outliers, and then you calculate the mean again. The median average deviation, the minimum, the maximum, the range, that's the distance between the highest and lowest values, the skew, kurtosis, standard error. So these are other summary statistics that you might find useful. But here's another aspect of the psych package that's really helpful. Remember that in the iris data set we had 3 different species, and we might want to separate out the 3 different species. So we can do that with the describe by command. So we have to spell it properly. Describe by command. And we first have to tell the data frame, and then we have to tell what column we want to use to separate out the different portions of the data frame. So we're going to sort by the factor, by species. So I'm using describe by iris, and then iris species, the classification variable. And when I do that, then I get 3 different printouts. I get one for setosa. There are 50 different rows for setosa, 50 for versicolor, and 50 for virginica. So the psych package can be very useful when you're calculating summary statistics, and it will give you some statistics that the built-in summary command will not in R. A couple of recommendations about R. One is that R is case sensitive. So it's a good idea when you are defining an object or a column name, just to use lowercase values. That way you never get confused as to whether or not it should be uppercase or lowercase. So I always use lowercase values. Obviously, the people that did the Irish data set didn't, because their names are capitalized. But if I had little s EPAL, then R would not be able to find that particular vector. So that's one thing to remember. And two, when we're describing objects, so if I wanted to do an object called CF, that's perfectly fine. So CF shows up here in my values here. But what happens if I do this? Well, I get an error command, because R does not like to see spaces when you're trying to define an object. So we don't want to have any spaces there. Neither do we want to put any sort of symbol that is used in arithmetic. So we wouldn't want to use the times, because that essentially is read as C times F. And again, that is going to confuse R. But if I wanted to put a period, that's perfectly fine. And I could also, and I tend to use that a lot if I have 2 or 3 words. And you can also use underline, and that works just fine. But one other thing you can't do is to start with a number when you're defining an object. So I'm going to get an error there as well. We're going to look at another data set now called the air quality data set. Again, looking at some summary statistics. So this is one of the ones that's built in. So air quality, and there it comes in up above. So we're going to do what we normally would do, to take a look at the characteristics of the data set. We'll do the stir command, and we see that there are 6 different columns. They all are numeric in some way. 5 of them are integers, and one of them is a floating decimal and numeric, as you can see. And they all relate to different components of the air quality. And we can also do the head command if we wanted to take a look at the first of the rows of data. And of course you can do the tail command as well. We can also figure out how big it is. We actually already saw that in the stir command here, but we want to see it directly. But there are 153 observations, 6 variables. Let's say that we are interested in knowing what the mean value of the solar radiation is. So remember, what I need to do is to say what my data frame is, and then to use the $sign and then give the particular column that I'm interested in. So I'm doing the mean air quality of solar radiation, and I run into a problem. I get an error. I get NA, not available. So R is not capable of determining with the present data what the mean value of solar radiation is. Well, let's run a summary on air quality, and we can see what's going on. What we have is the usual 6 data that we get, the 5-num system plus the mean. In ozone, we get 37 NA values, and in solar radiation, we get 7 NA values. NAs are missing values. They're not zeros, they're missing values. And R doesn't know what to do with a missing value. So it doesn't know whether how to treat it. Should it be called a zero? Should it be ignored? It's essentially throwing it back to the investigator to say, how do you want me to deal with these NAs? We have a way of doing that that's pretty straightforward. A couple of ways, actually. What I'm going to do before I do that is to show you a very useful technique, which is that I can attach a particular data frame, only one, but a particular data frame to R. R now is, as the default, is the air quality data frame. So that means that if I want to refer to the solar radiation column, I don't have to type air quality $sign solar R anymore. I can just type solar R like that, and it didn't give me an error that it couldn't find it. It knew where to find it. It still has this NA problem. Well, how can we get rid of the NAs? Well, a simple way to do that is just to use the NARM command, and all I'm going to say is that remove all NAs, and that should be a yes. So NA remove T. That stands for true. You can use big capital T, or you can use capital TRUE. So if I do that, and you remember up here under solar radiation that we had 7 NAs. So this was, we had 153 values altogether. What we're going to do is to remove those 7 rows that where the values were missing, and we're going to calculate what the mean solar radiation is. And look there, it ran just fine. So we got rid of those 7 NA rows, and we were able to calculate the mean. We are going to run into the same problem when we do ozone. This time we have 37 missing values. So let's do that as well. Again, since I've attached the air quality data set, I don't have to type air quality $ before ozone, but I'm still going to use my, and I'll just add the T that time. So here's the mean, and it ran as well. So we have a way of getting around the problem with the NAs. Now, you might be asking, well, wait a minute. When we did summary on air quality, we got values for the means for ozone and solar radiation. And when you do use the summary command, the summary does, in fact, remove the NAs for you. But if you try to do an individual statistic like mean or standard deviation, anything like that, then you're going to get an error message, and you're going to have to remove the NAs yourself. Now that I'm done with air quality for the moment, what I'm going to do is to detach it. So I'm detaching air quality, and it's good if you have more than one data frame open. It's better not to attach any of them, because sometimes you have the same column name in 2 different data sets, and you can get all confused that way. But what we're going to do is to look at a different way of getting rid of the NAs in a data frame. And I'm going to set up a second air quality data frame. I'm going to call this clean air quality. And I'm going to use a global command, which is to say, take the data frame air quality and get rid of any row that has an NA in it. So I'm going to get rid of at least 37 rows, and perhaps some of these rows that are missing, we have an NA in solar radiation, have a value in ozone, so we could lose up to 44 rows in our data set. And what I'm going to do is to put that into a new object that I'm calling clean air quality. Now let's take a look at air quality up here. I've got 153 observations. So I should see a reduction in the number of observations, that is the number of rows. So I'm going to run this command, and now I had to get rid of 42 of those rows. 42 of those rows. Now I can do the mean of solar radiation, except I can't do it like that. I have to specify it with the data frame. So I can do the mean of solar radiation. I don't need to do an NA.rm because I've already removed all the NAs from the data frame. But you'll notice that I got a value of 184.8018. But here I had a value of 185.9315. And you can see what happened is that this value here I am basing on 146 values, because I started with 153 and I told R, just get rid of all the rows that have an NA for solar radiation. And so I based my mean on the 146 observations. Here, in the second example with the clean air quality, I get a different value because I'm not basing my mean on 146 observations, but rather on 111. So I got rid of some really useful data, in fact 35 rows of data that I lost, not because the solar radiation was NNA, but because the ozone was NNA. So the take-home message here is that the NA omit, this global removal of the NAs, is useful, but if you're interested in a particular column, you're likely to lose a lot of information. So using the more directed na.rm equals true command is usually a better way to get rid of the NAs.